Last time we tried to introduce the influence of a flow convection on a given premixed frame because originally we give you the very idea one-dimensional premixed frame propagating in the premixtures. Now we try to shift a little bit to discuss about the other factor coming from the molecular collision, basically described by the diffusion process. That means we bring both influence coming from the one of from the microscope point of view. It basically backflow. The other factor will be introduced based on the the microscope structures for the collision molecules. Okay, now we are dealing with the diffusion process. When we go back to look at a little bit detail, especially for the flux structure for the one-dimensional flow, as one-dimensional flow, as I mentioned here, there is the two zones are very important to be emphasized near the premixed frame. One is definitely it's a reaction zone. They tell you this is the thin frame zones involving with the very strong chemical reactions, and very fast chemical reaction will be complete, which can be complete in this thin frame zone. In front of the reaction zones, we have a so-called preheating zone. When you look at the flow structure inside of the preheating zone, you can see there is a temperature profile, right? And the temperature will increase starting from the edge of preheating zone and increase continuously to reach to ignition temperature and finally to reach the final flame temperature because we complete the chemical reaction. As you look at this temperature variation in the preheating zone, you figure out there is the so-called temperature gradient, right? When you have a temperature gradient, then you will think about there is important diffusion transport need to be considered in the preheating zone. This kinds of diffusion transport, we call this a thermal diffusion or heat diffusion, described by Fourier's law. And if you have a temperature gradient and get involved with the thermal diffusibility, then you can estimate the heat diffusion strength from the flame to the upstream. Remember, the direction of heat diffusion of your flame, of your this premixed flame, actually is from the high temperature side to the low temperature side, which means the direction of heat diffusion should be point to the upstream region. Okay, this is the so-called heat diffusion or thermal diffusion. Conversely, you look at the concentration of reactants, including the fuel and the oxygen, you find out the concentration of reactants, they will start to reduce when the flow approaching to the edge of the preheating zone. Concentration continuously decrease for fuel and oxygens in the preheating zones, which means they show you there is the concentration gradient, and those concentration of reactants will completely consumed when the chemical reaction completes, except there has some additional reactants depth if the mixing is not under stoichiometric ratio. But you can see they still have a so-called concentration gradient occurs in the preheating zone for both fuel and oxygen. Okay, and this reflects this. There is the diffusion transport occurs in the preheating zone and can be described by so-called Fick's law. And Fick's law tell you the mass diffusion strength can be described by concentration gradient coupling with the diffusibility, mass diffusibility of your species you may have. Okay, but you can see the gradient tell you the high concentration area region is in the front of preheating zone, and most of the the amount of the concentration of reactants will be consumed, reduced the minimum value. And here you can see the direction for mass diffusion must come from the upstream side, point to the flame. Now you can figure out there is the two different kinds of diffusion process. One is the heat diffusion from the flame to the upstream. Okay. The other one is the mass diffusion from the upstream to the frame. Okay, for one-dimensional model, usually if you assume the the diffusion strength or diffusibility for heat and the mass, they are balanced, then we say this is a Lewis number equal to 1, right? This is a so-called Lewis number equal to 1. Lewis number is equal to lambda divided by rho CPD, right? Lambda divided by rho CPD means there is the ratio between the heat diffusibility and mass diffusibility, or you can say thermal diffusibility with the mass diffusibility. You can say heat or mass or energy or thermal, depends on. But they give you the same understanding. Okay, when when heat diffusibility balance with mass diffusibility, then we call this Lewis number equal to 1. That means the strength of the diffusibility from the molecules, they are balanced in this region. And the direction for the thermal diffusion and the mass diffusion, they just in the opposite directions. Okay, heat diffuse to the upstream. That means they just give you the idea is preheat the upstream premixture. Upstream premixture absorb heat, they start to decomposition, decompose to more active species, and the concentration reduce. And those kinds of diffusion process, they just balance if Lewis number equal to 1. This is an idea coming from the one-dimensional model, but when you put this model into a real situation, as I give you some examples, for example, the opposite jet flow, and also the jet flow or stagnation point flow, or even a flame propagation in a stagnant environment, you will figure out now the flame is not a one-dimensional flame. They will experience the movement, okay, the movement of your flame, and you will experience the flame surface change along with along the axial coordinate for jet frames, and you also find out there is a fragment experience the tangential velocity on their flame surface. Those kinds of different kinds of situations will give you some idea to think about how the balance between heat and the mass diffusion occurs in those circumstances. Now, this is the main point that I want to mention. Actually, those inference coming from the flow convection that means described by a material derivative, as I mentioned for the flow stretch, right? They always couple with the Lewis number effect. Lewis number effect will be described by the diffusion process, and I emphasize the diffusion process the diffusion process represents the interactives of molecules inside your mixtures. That means that we look at the interaction, the collisions of molecules based on microscope point view. Now we try to bring these 2 point view, macroscope and microscope, together to think about how these two factors, flow convections and also diffusion process, they couple together to influence your premixed flame. This is the main idea I want to mention here. Okay, now we are dealing with Lewis number. Okay, now which means that Lewis number represents the influence coming from the diffusion process. Okay, and the flow stretch represents the influence coming from flow convection. Okay, try to remember these two. Now they couple together. Okay, here before we introduce some experimental observations, I need to give you the definition. Try to remember those kinds of evaluation on the Lewis number quantity. Okay, now we go back to the basic definition for Lewis number. Lewis number is equal to lambda divided by rho CPD, right? Lambda divided by CP means this is a thermal diffusibility, and rho d is basically describe the mass diffusibility. Now here they tell you there is the two strengths of diffusibility compare and to be presented as a Lewis number. the denominator represent the mass divisibility, and the numerator represent the thermal divisibility. Okay. Now, when you usually you may think about, can you, if I want to estimate Lewis number, then you need to check the thermodynamic table to find out the thermal divisibility and the mass divisibility and count it, right? But an easier way, I tell you how to estimate the value of Lewis number by this way. Think about it. When you look at the mass divisibility, right? Because now you have a premixture. Look at go back to our previous French structure. Okay, here there is the two line, right? There is the two concentration line. One represent is the abundant species. The other one, smaller one, represent deficient. Okay, but usually the abundant one is a higher concentration compared with that for the deficient components. Usually the combustion strength, in this case, you can find out the combustion strength, the burning process basically is controlled by the deficient one. Because the deficient, if you do not have enough deficient reactants diffuse into your reaction zone, actually, even you have abundance of the other species exist in your friend zone, you still cannot have a chemical reaction, right? And when you think about the mass diffusion, which reactants will be important? Deficient one is most important. If when you think about how much fuel or oxygen should be diffused into your chemical reaction zone, really the governing concentration, the governing species basically is the deficient. Okay, and usually the divisibility can be determined by the size or weight of your molecules, right? Now you think about the mass divisibility, basically is inverse proportion to the molecular weight of diameter of your molecule. Okay, now you think if I put some estimation on the mass divisibility, then we'll think about this value will be inverse proportion to the molecular weight of diffusion component. Okay, now here the molecular weight of diffusion component in your premixtures will stand in the denominator. And you think about thermal divisibility. The thermal, that means that the molecule carry the kinetic energy, right? Because now your temperature is high, then the kinetic energy of your molecule will be high. Now they carry this thermal energy, kinetic energy of your molecules from the flame side to the upstream side. Who will carry this thermal energy? Actually, all the species can carry, right? We cannot restrict to the abundant one or deficient one, because all the molecules have the same experience in a high temperature region, has a very the same kinetic energy, which means the thermal divisibility will be influenced by all the species you have. Now you think about how to describe this one. Actually, this thermal divisibility can be described as the inverse proportion to the diameter or molecular weight of average in sense of the average value. Then here now you can use the average molecular weight to represent the strength of thermal divisibility. Definitely there is the inverse proportion. Now the average molecular weight will be put in the denominator. Okay, now this is the idea we can think about when you have a premixture of fuel and burn in the air, and you try to figure out or estimate how much of the Lewis number it may have. Okay, now I give you some practice here, and there is this is the table, and you can find out the exact thermal divisibility or diffusion coefficient D, and from the thermodynamic table. Okay, this is the exact value, and I try to give you some comparison, because those values can be found from the real data in thermodynamic table, and list the value for Lewis number is exactly can be found, and we just use the some estimation and try to evaluate approximately and try to do some comparison. Okay, the first one. If you think about the Dean methane air premixture, now you think about this room number can be evaluated approximately. Now this is a Dean methane, right? And which one is the deficient one? Methane is the deficient one. Then in the denominator here you have a 16, right? A molecular weight. But in the denominator you will think about the methane mixed with air. Air consists of nitrogen and also the oxygen, right? Both of them, the molecule is much higher than the molecular weight of methane. When you mix together, there is no possibility to let you have an average molecular weight smaller than 16, right? Should be larger than 16. Then you will find out the denominator, the value in this part should larger than 16. Then when you evaluate the comparison between 16 and the value larger than 16, then you find out the Lewis number here, this should be smaller than 1. Okay, be remember Lean methane air mixture. For example, you check with the data from the table, Lean methane air premixed flame, and here the equilibrium ratio is 0.5, it's very lean, okay, and here you can see Lewis number equal to 0.97. Very close to 1, but smaller than 1. But this is small value, small difference give you a big difference on burning intensity. I will tell you from this truth from the experiment data. Okay. The other way you think about for lean propane air premixtures. Okay. Now you do the similar way. Now the propane is a lean, right? And then you can put the molecular weight of propane is 44 in the denominator. And in the denominator, we think about for the average molecular weight for these mixtures, actually the air contains 28 nitrogen molecular weight for nitrogen and 32 for oxygen. Both of them more than the 44 molecular weight of propane, right? Therefore, in the denominator, the value should be more than 44. Then here you can see Lewis number larger than 1. For the lean case, the lean cases for methane air and propane air, they give you the just opposite estimation on Lewis number value. 1 for lean methane, then Lewis number is more than 1. But for lean propane, the Lewis number larger than 1. Okay, we check it. Lean propane here. Okay, the equilibrium ratio is equal to 0.55, and the Lewis number is around 1.82, larger than 1. Okay, and 0.97 and 1.82, actually you calculate from the exist data from the thermodynamic table. But we do some quantitative comparison, you still do the same results. Okay. You may try to think about for rich methane air mixtures, Lewis number bigger than 1. For rich propane air premixture, the Lewis number should be smaller than 1. Then you will see there is a couple, right? For example, you want to see the Lewis number smaller than 1, you may have those kinds of same behavior for the dim methane flame and for the rich propane flame. Be remember this as a set of couple, a couple set, and you can see they will show you the same burning characteristic. Okay, and for dim propane and for rich methane, both of them has Lewis number larger than 1, and for these two cases, they should have the same burning characteristic. I will describe later. Okay, now keep in mind, if you have a Lewis number larger than 1 means Lewis number larger than 1 means the thermal diffusibility is the strength for thermal diffusibility is larger than mass, because larger than 1, right? The strength from the denominator is strength than that in the denominator. Okay, Conversely, if Lewis number is smaller than 1, which means the mass is stronger than the thermal. Okay, be remembered by this way. Now we try to look at several experimental observations. Now the first one, as we're familiar with this opposite jet flow or stagnation point flow, look at the inference coming from the Lewis number here. You can see this is an example of propagating, a flat friend propagating in a stagnation point flow, right? This is a stagnation point flow. If you can still think about the friend propagating in the counter flow by this way, by opposite jet flow, if you consider this is a virtual stagnation plane, not a stagnation surface, a virtual stagnation plane between two jets, then you can see there is the identical plane in the upper flow, right? There's a double plane, okay? And both planes experience the same situation as one plane exists in stagnation point flow frame. Okay, now look at here. We try to think about our problem. If you choose a so-called string tube, okay, now we are talking about a steady flow. We continuously supply the premixtures and impinging them onto the stagnation plane, stagnation surface. And this premixture is combustible. We have some mixing of fuel and oxygen together, or even air together. Then they impinge it, they ignite it, then you will flat flame exist in certain position of the stagnation point flow. Okay. Now think about the balance between the mass diffusion and the thermal diffusion or heat diffusion. This is a frame, okay, and you can assume there is a boundary of your preheating zone. Okay, look at here, this region is a preheating zone. Now inside of the preheating zone, you will think about that there is a concentration gradient and also the temperature gradient. Then you will see we need to discuss the strength of diffusion for heat and mass, and to look at did they have a balance or unbalance. Okay. Now you will think about now if you have a fresh flow coming from the very far upstream, then they approaching to the edge of preheating zone here. Okay, up to here now the the flow process actually will be governed by diffusion, right? Mass diffusion will point to the flame surface. This is the arrow to represent the mass diffusion directions, okay? And you will find out because all the mass is defined by a confined string tube. You remember the string tube do not allow the mass flow closing the string line, right? They are confined because the actual velocity, the tangential velocity were tangent to the string line. You do not have a so-called normal velocity to let your flow inside your string tube flow to the outer region. Okay, which means that when you have a premixtures along with moving along the string tubes, all the mass come to here. Then they will diffuse directly to the flame, will be restricted by the string tube. Even the flame region will become larger, right? Which means the mass diffusion actually they are fully be used to support your burning flame. And you will find out, you will ask the question because all the mass will be distributed to a large region, right? But you remember here, there is some mass coming from the outer side. They still have a diffusion, right? Flow cannot move in through the string tube. That means that definition coming from the flow velocity, basically corresponding flow convection. But molecule for flow molecule, as I mentioned earlier, the diffusion process that you has a possibility to across the string tube, which means they have additional mass diffusion to this enlarged flame surface, which means the mass diffusion is always be confined in this flame surface. The support is it still will go through the flame surface. Conversely, if you look at heat diffusion will carry heat from the flame surface to the upstream side to preheat your the upstream premixture, right? But unfortunately, when you look at the edge of your flame surface near the stream tube, those heat diffusion coming out, when they preheat, when they heat diffuse to this amount of premixture, actually those heat can be carried along with the stream tube to the further downstream. They may not have a chance to preheat to the further upstream site because the flow convection is just in opposite directions with the direction of heat diffusion. In this case, the direction of mass diffusion is accompanied with the direction of flow convection. They are along the same direction, but the heat diffusion has the opposite direction compared with the flow direction. Those heat diffused out will be carried to further downstream back. Okay. Now, when you look at this kinds of mechanism, you figure out in the stagnation point flow, if you have a premixed flame here, actually this flame will be suffered by heat diffusion, right? Heat diffusion give you a negative effect, but mass diffusion will give you a positive effect. Okay, now you think about when you bring these two effects, one is the negative one, the other one is the positive one, and we compare together. Put the Lewis number as an indicator. Now we try to identify the influence coming on this imbalance of heat diffusion and mass diffusion. For example, here, if you look at Lewis number bigger than 1, remember Lewis number is equal to heat diffusion divided by the mass diffusion. Now, in this case, they tell you Lewis number bigger than 1, that means the influence coming from the heat is stronger from the mass, right? Okay, unfortunately, here the heat diffusion is negative effect and the mass diffusion is a positive effect. But positive effect is in the denominator, okay, which means that now the heat diffusion effect is much stronger. The negative is stronger. Negative effect is stronger than the positive effect. Now the flame is weak. Okay, now flame is weaker compared with the Lewis number equal to 1 condition. Now you go back to see the structure described in the right figures. We start from the ideal case. If Lewis number equal to 1, okay, this curve represents the chemical reaction rate you usually understand, okay, and you can do the experiment. This experiment tell you, okay, you have a premixture with a Lewis number equal to 1. Now this is a chemical reaction rate distribution represent the reaction zone or flame zone, right? Now you try to increase your injection velocity. As I explained earlier, when you increase the injection velocity, you will push your flame closer to the stagnation surface, right? For the case of stagnation point flow, this is a solid surface, then they will give you some heat loss. Okay, will give you some heat loss. Now, when you increase your injection velocity as much as possible, you will find out your flame will shift from the right-hand side, approaching to the left-hand side, approaching to the wall, the stagnation surface. Okay, and then you can see the strength of chemical reaction rate actually in this plot to show you there is almost the same, right? Except when this flame is very close to the stagnation surface. As I mentioned here, for stagnation point flow in this region, there is a solid wall, okay? When this flame closer and even touch to this plate, then they will have a very strong heat loss, and you will see there is some region is broken because they do not have a chemical region to finish the chemical reaction. Now you may suppress the burning intensity in this region. Then finally there will be extinction, and this extinction basically coming from the heat loss or incomplete combustion for the stagnation point flow. But for the counter flow, you try to imagine for the opposite flow, then you will have they have double flame, right? Identical premixed flame. when you increase the injection velocity, these two frames will closer to the virtual stagnation plane, right? Virtual stagnation plane is different from the solid plates. Virtual stagnation plane will not give you any heat loss, but they will give you the chance, because these two frames, when they cross, this incomplete combustion may be the most important one, because they do not have a space to finish chemical reaction. Then they collapse together, then flame extinction. Okay. For the stagnation point flow, for this case, there is two reasons to extinction the propagation flame velocity as you increase the injection velocity. Here, I explain again. The flame starting from a certain distance away from the stagnation surface. When you increase your injection velocity, this flame will move closer. Up to here, they still remain a steady burning very nicely. But when you push them more closer to the stagnation surface, there is the two influences coming from the stagnation surface. One is the heat loss to the solid surface. The other one is the incomplete combustion, because we do not have enough space to finish the chemical reaction. Okay, and this is two reasons for the extinction of your premixed flame in the stagnation point flow. But for the opposed jet flow, you need to try to image this stagnation surface. Basically, it's a virtual. Then you may not have a so-called heat loss. They just the only reason to make the flame extinction is incomplete combustion. Okay, incomplete reaction. This is the reason for the extinction for these two cases as Lewis number equal to 1. But in this in this process, you can see Lewis number equal to 1, heat diffusion is balanced with mass diffusions, then the chemical reaction rate will remain constant unless they're approaching to the stagnation region. Okay. Now we go back to the first case we described as Lewis number bigger than 1. Okay, I repeat again. Lewis number bigger than 1, that means that the denominator, the heat diffusion is much important than that mass diffusion in the denominator. Okay, then in this case, heat is stronger. The influence coming from the heat is stronger than that coming from the mass. But unfortunately, for this stagnation point flow, the heat has a negative effect, but mass is a positive effect. Negative effect is stronger than the positive effect, then flame become weaker. This is the case. Tell you Lewis number bigger than 1, the upper figure. When you're increasing the stretch means that you're increasing the injection velocity, right? Continuously, the flame will move from the upstream side to closer to your stagnation plane, as that described for Lewis number equal to 1. But in the process of approaching to the stagnation surface, you will find out from the figure the chemical reaction rate become weaker. Okay, this is weaker. Finally, there will be extinction. Actually, they still have enough space to finish the combustion, right? And we call this as a complete reaction. But you have a complete reaction, but why not? You have a complete reaction? Why the flame still be extinction? Actually, this is extinction by flame stretch coupled with Lewis number. Okay, because the heat loss continuous, the negative effect, not heat loss, the heat diffusion. Yeah, sometimes you can say that heat diffusion is, in this case, some kind of loss, because heat diffusion to the outer region of your string tube and be carried out, they cannot use this heat to preheat the upstream side premixtures. That means some kinds of heat loss through the flow moment. Okay, and this extinction basically influenced by the Lewis number effect. Okay. Conversely, we look at a case for the Lewis number smaller than 1. Here they tell you now the mass is stronger, right? The denominator, the mass diffusion is stronger than the heat, which means the positive effect is stronger than the negative effect. then the frame should be stronger. Okay, this is an example here. Okay, now you can see for the stagnation point flow, for the case of Lewis number smaller than 1, when you push your frame to closer to the stagnation plane, the chemical reaction rate actually they be enhanced continuous to a larger value, but unfortunately they still need to attach to the stagnation surface, and here this will cause the frame extinction because there is an incomplete reaction. And the second reason for the stagnation point flow is a heat loss. Okay, and both influences will give you the will lead to the extinction condition. But for the opposite flow, incomplete reaction is the only one of the reason. Okay. Now I think from these kinds of plot, you understand how to describe the inference coming from the Lewis number coupled with flow stretch. Remember, for the stagnation point flow or opposite flow, the frame always under positive stretch. Okay, this flow is under positive stretch. Now this positive flow frame stretch coupled with Lewis number effect will give you this different kinds of variation, and you try to remember it, and we will have some experiment results to show you later.